Hi friends, welcome on board for another project. This time I decided to design this board for you. It actually consists of two parts. The first part is an AC to DC flyback converter. So this circuit here is the AC input, universal in the range of 85 to 260 volts. And this side is the output, 12 volts DC, 6 watts maximum. And the second part is this circuit. It reads the temperature through a 10K NTC sensor, and the sensor is connected to this XH connector. And from the sensor, for example, this one. As you know, they are manufactured in different shapes. Even some of them have a hole in the front that you can mount the sensor on a heatsink and read the temperature of that heatsink. So as I said, it reads the temperature, and based on the temperature, it drives, or it can drive, two fans simultaneously. And as much as the temperature increases, the rotation speed of the fans also increases. The fans, for example, this big deep cool fan or this small one, doesn't matter. Just the voltage of the fan should be 12 volts, as most of the fans are like this. They are rated at 12 volts. So it works based on PWM. As the temperature increases, the duty cycle of the PWM also increases. It means higher rotation speeds and vice versa. This is a standalone device, so it means you don't need to change or modify the device that you want to mount this board in that device. For example, if it is industrial or homemade, for example, a powerful amplifier, you don't need to change anything, because if you change that device, you might void the warranty, or if any malfunction happens in the future, they will say you did that. This device is totally independent. Just you need to connect this side to the mains and this side to the fan and the sensor, and the sensor on the heatsink or whatever object that you want to control or cool down or maintain its temperature within the range. I think you got the motivation behind this circuit. As usual, I designed this board also using Altium Designer, and I have uploaded all of the project files, including the code for this microcontroller, in my Altium 365 cloud space. So just follow this link and register on the Altium 365 website. Then simply follow this link and download all of the project files for free. I will explain the board just briefly here, because in the next step I will open the schematic and PCB in the Altium 365 and explain it in details. As I said, here is the AC input, controller, bridge rectifier, snubber, main capacitor for ripple reduction. This is the transformer, optocoupler, the output side, the Schottky diode, SMC type, and these two capacitors for noise reduction, the microcontroller, MOSFET, and this is the ISP interface to program the microcontroller. This is the backside. Just these two passives, these two resistors, and this diode on the backside. You can see the isolation gaps and creepage areas to follow the high voltage IPC standard. If I show you the bare PCB board, maybe it's easier for you. You see the isolation gaps? Yeah. I think that was the brief explanation. In the next step, I will go through the schematic and PCB. So what's going on here? Where I am? Here is the home page of my Altium 365 cloud space. As you see, I have uploaded all of these projects so far, and the rest, these ones, belong to the Altium itself. You can use them as a sample. But wait a second, you can create your own space for free, the same as me. Just follow this link in my YouTube video description and register on the Altium 365 website. then come here and upload your PCB project and share it with your friends and your colleagues. But you may ask, what's the catch? What's in it for me? The main benefit of this Altium 365 is, except for many other features, when you're working on a PCB project, and especially if that PCB project is complex and you are working in a team, for example, a team member designs the power supply, a team member designs the digital part, microcontroller and the connected circuits, another team member designs the RF part, Wi-Fi, Bluetooth, and similar. If you communicate traditionally using email, of course, you will live in a mess of arguments, discussions, PCB files, and many other things. You waste your time, waste your resources, and as a result, you waste your money. Your project will be delayed. But here, all of you are connected on a single PCB project. If I, for example, as a digital designer, make a mistake somewhere on a PCB layout, you will put a notification there and you will say, for example, change that resistor to 10K. If I apply that update, you will see instantly live on the cloud. You will not exchange anything. So you can imagine how much time you will save in this mechanism and on this platform. So just register and check other features and suggest it to your friends and your colleagues. You will enjoy that platform. This is the latest project, by the way. Let's go to the schematic. This one is the PCB layout, and this one is a 3D view of the PCB board. Let me zoom in the schematic and start to explain from here. So here is the AC input. The AC input is universal in the range of 85 to 260. I made a typo mistake here. You know what I mean, 85 to 260 volts AC. It goes through this fuse resistor. The package is MELF and the size is 309. Why a fuse resistor? It has two benefits. First, of course, it is a fuse, and the second, it can limit the inrush current, and also it may create an RC filter with this capacitor and reduce the high frequency noises. But you can use a fuse resistor in high power applications, but for small ones it's a wise choice. Of course, a bridge rectifier to convert the AC to DC, and this capacitor for ripple reduction. Be careful about the ripple current rating of this capacitor, because if the ripple current is low, this capacitor will dry out too soon. You know, one good feature of this Altium 365 is when I put the cursor on the net, it highlights the net like this. Anyway, the high voltage DC line comes through here and goes to the transformer, and another side goes through this RCD snubber, and the controller switches the other side of the transformer. So we don't have an auxiliary winding here. This switching controller gets the voltage from here, the supply voltage. This is one main advantage of this DK106 controller. What this RCD snubber does, it dampens the spikes on the perimeter of the transformer, which is created by the leakage inductance of the transformer. So we have to use something like this RCD snubber to reduce the spikes of the perimeter for the main reason of protecting the internal MOSFET of this controller. Sometimes the MOSFET is outside, but in this case is embedded inside the controller. But also this RCD snubber can reduce the EMI, but you have to investigate this on the oscilloscope and check if the ringing on the edge does not have any sharp edges. In that case, your RCD snubber does two good jobs, except for protecting the MOSFET. So here is the optocoupler, and the output goes through this feedback, and the controller senses the output galvanically through this optocoupler. So any changes in the output will be reported to the controller, and the controller modify the duty cycle of the PWM pulse. Of course, it is more complex than this, but the main concept of this mechanism is like this. Here is the output side, the Schottky diode. I selected the SMC package, the first stage of the noise reduction through this C5 capacitor, this LED to show there is a correct voltage level here, of course to indicate that the circuit works correctly. Then one, I can say, a relatively strong RC filter, 100 ohm and this 1000 microfarad. Why? To reduce the noise for the rest of the circuit, which we have a microcontroller here, and this microcontroller uses an ADC. So we have to reduce the noise and spikes on the voltage rail as much as possible. But here we have a space, we have a possibility to use a strong RC filter like this. Of course, and of course a linear regulator here to provide 5 volts rail for the microcontroller. The microcontroller reads the temperature through this ADC line, and this ADC line is connected here. It reads the temperature variation through this NTC. The NTC is 10K, so 10K by 10K is a voltage divider, so temperature changes will affect the voltage level, and this ADC reads the voltage levels, and then it drives the fans through this net F speed, and the fans are driven through this MOSFET and the PWM pulse. So the duty cycle of the PWM pulse will affect the rotation speed of the fans. This diode protects the MOSFET against the reverse currents of the fans, but you should use a Schottky type. Because why? Because the frequency of this, the switching frequency on this MOSFET is 25 kHz. The frequency is high, so you should use a Schottky diode to get all of these small and high frequency pulses on spikes. Otherwise, if you use an ordinary diode here, you might see some, I can say, it might not protect the MOSFET as good as a Schottky diode. This is a good term. Of course, an ISP header to program the microcontroller. The microcontroller is ATtiny13. A pull-up resistor on the reset pin. I think I covered everything. Of course, 2 decoupling capacitors for the VCC of the microcontroller. A Y capacitor. You know better why I put a Y capacitor here. So that's fine. Let's go to the PCB. Of course, a 2 layers PCB board. You can see the isolation gaps and creepage areas here. One here, one here, one here, another one here, another one here. Let me disable the top overlay or the top overlay or a silk screen. So the red is top and blue is bottom. Let me disable the top. So you see I have engaged engaged the ground to the bottom layer. So and this decision is to reduce the length and impedance of the ground path. So this is the ground, and if I just show the top, yes, you see even for the top I have followed the same concept, and these vias also used for the same purpose, to reduce the length and impedance of the ground path. The benefit means at least lower noise and better performance for the circuit. Let me enable the layers again. There we go. Nothing special remains here except that here the length between the drain or the driving pins of the controller and the pin of the transformer should be as short as possible. So this length should be as short as possible, because you will see, or we will have high switching currents and high switching spikes here. If the length is high, it will affect the radiated emission level of the circuit. The same thing should be followed here. This RCD snubber should be placed as close as possible to the transformer. The similar thing for the output. The loop from the Schottky diode to the ground pin of the first capacitor should be as small as possible. This loop, I mean. You see? From the input of the Schottky, it goes through the first capacitor and to the ground. And this ground is as close as possible to the ground pin of the transformer. This loop is very important, should be as small as possible. The microcontroller ISP interface, fan 1, fan 2, and NTC Y capacitor. If you have any questions, I might miss something, but if you have any questions, let me know in the comment section. This is the 3D. If I show you the backside, everything is pretty clear. Just these two passives, these two resistors on the backside, and this Schottky diode, if you remember, for protecting the MOSFET against the currents of the fans, LED, and everything. Beautiful, isn't it? Let's go to the coding section. I will explain the code. So I will explain the code in this section. The compiler is Arduino IDE version 2.3.4. I don't think you will have any problem with future versions also. Let me remind you that you don't need to write the code from the YouTube screen, because I have provided the code also to download alongside with the PCB files. You just need to register on the Altium 365 website. That allows you to follow the second link in the YouTube video description and download all of the files for free. So to start the coding, first we should prepare the Arduino IDE to compile the code for the ATtiny13 microcontroller. So first come here to this GitHub named Microcore and install the ATtiny13 board manager. My assumption is that you know how to install the board manager, because it's pretty easy. So if you follow the instructions correctly, you will see the ATtiny13 here. So from the tools menu, board, and Microcore and ATtiny13. It also gives you these options. The clock frequency is important. Here, the clock should be set on 9.6 MHz and internal clock source. This is important. Let's go to the code. So the delay function and definition for the CPU clock frequency. Nothing very much here. The important point is here. I use this code to initialize the PWM, phase correct PWM with no prescaler. The frequency of the PWM is like this, 9.6 MHz divided by 192, because OCR0A is 192 divided by 2 means 25 kHz for the frequency of the PWM. The rest is pretty easy. Here we read the ADC values, or I can say the temperature values. If the counter or the quantity of the values is equal to 15, we make an average of 15 values. This is to reduce the noise in the data and fluctuations. And based on that ADC value or the temperature, I can say, we make a decision here. If the temperature is lower than something, we don't need any rotation in the fan, so OCR0B is 0. if the temperature is higher than something, we will make a decision by this map function. So this map function assigns the PWM duty cycle with the temperature. It's easy. This is the highest temperature, my highest temperature or the highest duty cycle for the PWM, 230, 192, okay, and the lowest temperature or the highest ADC, and the lowest PWM duty cycle. One question here you might ask, why not I put 0 here? Why? Because you know what, for the 12 volts fan or the 12 volts fan won't rotate if the voltage is lower than 6 or 5 volts. So it does nothing if I put 0 here. So 60 is around 5 or 6 volts. So this is the rotation, minimum rotation speed for the 12 volts fan. It might be different for your selected fan, so you can also modify this value. In my case, 60 was the initial rotation speed, or I can say the slowest speed for the fan. Otherwise, the fan, if I put lower than 60 here, the fan won't start at all because the voltage is low. I think you got what I mean. And here, of course, I put the out in the OCR 0B. And if the temperature goes higher than this one, of course, we need full rotation or the highest duty cycle for the PWM. This is what we can do to reduce the temperature or to cool down the heatsink or whatever. Because we have engaged the timer for the PWM, we have to use this function, delay millisecond, this type of function, and I put 20 millisecond delay here, and this clock frequency for the CPU increases the accuracy for this delay millisecond function. So the code is as simple as this. If you need to modify anything, just do whatever you like. You have the code and have fun. Alright, I have prepared this picture to handle you all the necessary information you need to build the transformer. So the left picture shows the size and dimensions for the ferrite core, and the ferrite core is E1985. It is pretty famous and easy to find. In the middle, you see the specifications for the primary and secondary windings. The inductance of the primary should be around 3.1 millihenry, and it made of 130 turns of 0.2 millimeters of magnet wire. The secondary is like this. On the right side, you see a picture of the bobbin, and the bobbin has 3 pins in the primary and the 3 pins for the secondary. Please double check the size and dimensions for the bobbin. The spacing between the pins from this side to this side is around 11.3, and from here to here is around 4.7 millimeters, or I can say 5 millimeters. Be careful because there are a lot of similar bobbins on the market, and you should find and buy this one. So I think this information is enough. Let's go to the testing section. Alright, now I'm gonna test the circuit. It's pretty easy. Just connect this terminal to the mains input. You can use 1 or 2 fans. At the moment, I connected only 1 fan, this 12 volts deep cool fan, and this XH goes to this 10K NTC sensor. My perfume also does a good job here to keep the wires and the board on the table. I'm not sure if you can see this LED here. When this LED lights up, it shows the power supply works correctly and there is a correct voltage at the output. If you can hear a noise at the background, it's because of my other station, because I want to warm up this NTC and show you the fan starts to rotate. Now I warm up the sensor little by little and you will see the fan starts to rotate. There we go. Go, 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 go. Yes. So it shows the temperature of the NTC passes that threshold I mentioned in the code. And as the temperature increases, the duty cycle of the PWM pulse increases. It means higher rotation for the fan and vice versa. So pretty much that's it. You can change and modify all of these thresholds and rotation speeds in the code. I hope you liked this video. Use this circuit in your devices and don't forget to share and subscribe and show you this project to your friends. So have a nice day. Take care.